Okay. You say a couple of words about the homework for next week, due next Friday. So I introduced this last time, this notion of the radical of an ideal, with that crazy square root symbol. It's all the crap in R that there's some power of X that lands you back in the ideal R. I claimed that this was an ideal. I want you to show it. So you need to show me that this is an ideal. So you need to show that it's a subgroup of R. That is, when you add two elements or subtract two elements, it's in there. Associativity, the identity element 0 is in there, and so forth. And you need to show its vacuum. Number 2, R is a commutative ring of 1. And by the way, I said that for completeness. You can always assume that unless I tell you specifically otherwise. Show any ideal that's maximal. Remember what that means, as big as possible. It's always a prime ideal. That's defined. Show that any prime ideal is radical. And then C, show that not all radical ideals need to be prime, and show that not all prime ideals need to be maximal. By the way, we're going to talk about some examples very early on, and we'll help you immensely with that problem. And number 3, this is kind of a fun little ring. It turns out, if you look at number D, not all prime ideals need to be maximal. And we'll probably see an example of that today. However, if R is a finite, then an ideal is maximal if and only if it's prime. So they are the same thing, even though prime is a weaker condition than maximal in general. They're actually the same if you're in a finite ring. Okay, any questions? So let's kind of pick up where we were last time here. Okay, so it's not a hurry. Let me do this real quick. Remember, it's commutative ring of 1. This is just one of our little playgrounds where you can add and multiply. Suppose I and R is a proper ideal. I want this to be actually not all of the ring. Number 1. So what it means to be a maximal ideal is it's as big as possible without being a whole ring. That means if you try to squeeze another ideal between I and R, then it's either I or R. There's no other way to do it. Oh, no one. Talk to me after class. Yeah. What it means to be prime is if the product of two things in the ring end up in I, then one of those two things has to be in I. 3. I is radical if x to the n is an I, implies that x is. So let's, okay, so there are the concepts. Let's see if we can try to figure this out. Let's do Z6 first. The ideals are subgroups that suck everything in, right? So I'm going to just go to the trouble of listing them all here. So there's actually there's the ideal that consists of the whole ring, and I'm going to throw that one out. That one's not proper. That's it. By the way, I can use Lagrange's theorem here to help me get the ideals, because how many elements are in this ring? There's 6 elements. And this ring, first and foremost, is a little abelian group. So the only subgroups have to have order dividing that, right? And so that helps me. I mean, there's no ideal with 4 elements in it because 4 doesn't divide 6. So here's one ideal that has 3 elements in it. By the way, we've seen already that this is a subgroup, but it clearly sucks stuff in, right? Because if you multiply 1 bar times any of these things are still in here, and 5 bar, and notice if you multiply 3 bar by anything in here, you get 0, which is still in there. Right? This is also a little subgroup, and it also sucks because if you multiply, this is 1 and minus 1, so if you multiply anything in here, it'll still be in here. 0 works. Anything that's even multiplies that to 0, and if you multiply anything by 3 bar, it's still 0 or 3 bar. And of course, let's classify this. By the way, this is not an exhaustive list of types of ideals. And in fact, if I give you an ideal at random, it's probably none of these. How about the 0 ideal? Is it maximal? Certainly it's not maximal because it's contained in larger ideals. In fact, both of these, right? So not maximal. Is it prime? So let's look at the definition of prime. What it means to be prime is if you multiply 2 things and you end up there, then one of those 2 things has to be in there, right? Can anybody think, can you multiply 2 elements in that ring and it lands you in here without either one of those being 0? You certainly can, right? Notice that if you multiply 2 bar times 3 bar, it's in here, but neither 2 bar nor 3 bar is in there. So this is not prime either.
So if they were in there, then it would be prime.
Notice that 2 times 3 is 0, but neither 2 nor 3 is in here, right? Neither 2 nor 3 is 0. So this is not a prime idea. Is it radical? Well, what you got to ask yourself here is to test for radical. Let's translate to this particular ideal. What it says is if x to the n is 0, that means x is 0. Is this true here? What does it mean for x to the n to be 0? What's the word we use there? It's a nilpotent, right? But that doesn't happen here, right? Because remember, to be nilpotent in this, you have to have a factor of 2 and 3, right? Which means 0, right? Notice the powers of 1, no way it's going to be 0. The powers of -1, no way it's going to be 0. The powers of 2, 2, 4, 2, 4, it's never going to be 0. The powers of 3 are 3, 3, 3, 3. And you got a similar thing with 4, right? It's 4, yeah, 4, 4, 4, like that. So this is radical.
Did you think of that too, as like 0 is always a nilpotent, or 0 always a 0 advisor?
0 is always a 0 advisor, and it's always a nilpotent too.
Okay, so then will 0 bar always be radical?
Really, not necessarily. I'll give you another example. These are both maximal, right? The only ideals bigger than either of these that contain either of these is the whole ring. Yes.
I just so I'm not confused. Is there any evidence they take I3 and I4 that you go there? Are they?
Oh, I'm sorry. I did call this. Yeah, I call that 3 or 4. My apologies. You're right. These are maximal because there's no bigger ideal than this that you can squeeze between that and the whole ring. And they're also prime and radical.
Can you explain again why they're maximal?
Right, because what it means to be maximal is there's no bigger ideal that this is contained in, right? Because anything bigger than this is the whole ring. So you can see from this table right here. So it's as big as possible. Now let me address your question here. Let me change my example. Now I'm doing things mod 4, right? Notice the ideals here. It's not proper. And there's actually only 2 ideals. This one is maximal. And you can check it's prime and it's radical. We're going to see later today that any maximal ideal is prime and any, well, actually, you show that in the homework, but it will follow very quickly from the theorem that I gave you today that any maximal ideal is prime and any prime ideal is radical. This one, 0, is none of the above. And the problem is notice that 2 bar times 2 bar. The 2 bar is not in there. Okay. Any questions? Let's do one with infinitely many. Here's a more sweeping one. Let me recall for you, and this will help. The proper ideals are just multiples of z, right? So the multiples of 2, the multiples of 3, the multiples of 4, etc., etc. Anybody want to guess what the maximal ideals look like? Well, let's kind of spitball a little bit first. What about the multiples of 6, right? So these are all multiples of 6. 0, 6, 12, 18, no negatives, 6. Is that maximal, or is there a larger ideal that you put it? Yeah. Right, you picked them both out, right? This one is actually every multiple of 6 is a multiple of 3, and every multiple of 6 is a multiple of 2. And so actually, these are genuinely bigger ideals that contain this, right? Notice 2 is here, but not here. 3 is here, but not here. Now, let me ask you this. What about these? Are these maximal? So 6 is not maximal because I put it in a truly larger ideal. What about these ones, the 2 and the 3? Are they maximal? That's correct, because suppose that 2z, for example, is contained in some other nz. What does that mean? This means that n must divide 2. Correct? So you even got the reason right, right? What divides 2? Only 2 or 1, right? And if you go with the route of 2, it's the same ideal. If you go with the route of 1, it's the whole ring. Everybody agree? So this is maximal, and the only thing that we depended on there was the fact that 2 is prime, right? Same argument will work for 3. Everybody agree with that? Anybody want to guess what the maximal ideals are here? They are PZ, where P What about the prime ideals? How about that? Well, see, what does it mean to be prime again? It means that A, B is in NZ, implies A is in NZ. Huh. So let me translate this into something that I can maybe wrap my head around a little bit. AB is in NZ means that A is in NZ or B is in NZ. I need to discover some properties of NZ. So another way to put this is A times B is a multiple of N. That is, AB is divisible by N. Means N divides A or N divides B. Anybody know numbers that happens to have? So really what we're searching for, here's the property that N has to have. If it divides the product of 2 elements, it must divide one of the elements in the product. Anybody know what kind of number has that property? Does 6 have this property? Six divides 2 times 3, but 6 does not divide 2, and 6 does not divide 3. Okay, so 6 doesn't have that property. Does that example give you any inspiration what kind of numbers have that property? Yeah. Positive primes. So the prime ideals are PZ, where P through 0 is prime. And there's one more. I missed one. Anybody know what it is? There's one more ideal, but this does not cover this prime in the integers. the zero ideal. That one there is actually prime in the integers, because let's think about what this means. What does A times B in the zero ideal mean? It just means A times B is zero. Now, if you got two integers and their product is zero, what can you tell me? One of them's got to be zero. That means that zero is a prime ideal. This one's a little bit harder to wrap your head around, but I think we can figure it out. What are the radical ideals? So remember, what we need is you notice x to the n, well, let's look at 6. I wonder if that's a radical ideal. What does it mean for x to the n to be in 6z? It means that if I take x and I jack it up to a high enough power, then that high enough power will be in 6z, right? What are the distinct primes that divide 6? They're 2 and 3. Everybody agree? So if there's a big enough power of x that's in there, then x has to have a factor of 2 and 3 in it. So this actually is radical. X to the n has a factor of 2 and 3. Right? So x has a factor of 2 and 3. You gotta love those primes, right? Because if x to the n has a factor of 2 and 3, then by the fundamental theorem of arithmetic, x has to have a factor of 2 and 3, which means that x has a factor of 6. So 6 is radical. Let me ask you this, what about 12z?
Six is radical because
If you have any integer x and a large power of x ends up in here, then that must mean that large power of x has a factor of 2. So that means x has a factor of 2. That large power of x has a factor of 3. So x has a factor of 3. So x has a factor of 2 and a factor of 3. And 2 and 3 are relatively prime, so it has a factor of 2 times 3. Right? So x has a factor of 6. So if a large power of x is in here, then x had to be a multiple of 6 in the first place. Now, what about 12z? Agreed? But 6 is not in 12. So this is not radical. What's the difference here? Anybody want to make a bold conjecture on what the radical ideals here from?
or not one distinct, but like, find number only once.
That's very good. So here's what has to happen for NZ to be a radical ideal. N is P1, P2, PI prime, and all different. And again, I left one thing out. Anybody want to guess what the road radical ideal is? 0. That's exactly right. So that's what notice that these are all slightly different. The maximal ideals are in Z, where it just, we sometimes say this is generated by P. So it's just multiples of P, where P is a positive prime. The prime ideals are all those maximal ideals, and then you've got this other road prime, 0. And the radical ideals are all products of primes, where all the exponents are less than or equal to 1, and n equals 0. Notice that in this particular example, and actually in the examples we did earlier, any radical ideal is prime, because 0 is prime, and certainly PZ, that's just with k equals 1. So got that covered. And notice that any prime ideal, any prime ideal is radical. I'm crazy, because if you have a prime ideal here, that's this case k equals 1. It's not true that every radical ideal is prime, because, for example, 6z. So if you've got prime, you've got radical. Notice if you've got radical, you've got, if you've got maximal, you've got prime. And this actually is true in general. Okay, so I'm going to give you a proposition here. I'm going to couch this, and I'm going to define, in this, I'm going to define some operations on ideals. Proposition 728. We're going to let I1, I2, IN, and R be ideals. Then so are. So here's a way that you can build new ideals from old. Number 1. So are these two ideals. The first thing says if I take a collection of ideals and I intersect them, I get a new ideal. We've seen this about groups, actually, and this follows for ideals too. And I think I'll let you see if you can figure out why that's true. But this other one, this is the product of ideals. Anybody want to guess how this is defined? Right? I mean, I just introduced this notation here just out of the blue. I didn't even tell you what this means. So I guess I better tell you what this means. What do you suppose it means to be I1, I2, IN? I want to guess. Well, I would hope that what this was is this is like a product with X1, I don't want to space that out, X1, X2, Xn, where X, I, Xj. I mean, wouldn't you hope that what this means is something out of I1, something out of I2, all the way to something out of IN and multiply? Right? That's what I hope that notation would mean. Unfortunately, I can't do that because this usually doesn't make an ideal. Because the problem is ideals have to be closed under addition. So here's what people in ring theory do when they get disappointed with multiplicative things that aren't closed under addition. They're lazy, lazy people, so they just put a sigma in front of it. So this is, let's see, I equals 1 to k of x I1, x I2, x IN. So what it means to be in this product here is that it's just a collection of, it's just a sum of products that look like this. And you usually need that sum here.
So the x's, is that just like one element out of the ideals?
That's right. And then you have to add them up. Let me
How do
give you
know which element?
any one you want.
Oh,
It's just any collection. Let me give you a concrete example. So, let R be, let's see here. Yeah, roll. So let R, so here's what this notation means. This is polynomials and two variables over the real numbers. These you played with these things in Calc 3 a lot when you did max-min problems and cross multipliers and all that kind of thing, right? And give you a bunch of these polynomials that have two variables in them, right? What happens when you take two polynomials and two variables and add them up? You get a bigger polynomial and two variables. What happens if you multiply polynomials and two variables? You get another polynomial and two variables with bigger degree maybe, but this is actually a ring. So this notation is here's a simple way to put this. These are all polynomials and two variables that have a factor of x in it. So I can pull an x out. This is actually an ideal, right? Because what happens when I add two things with a factor of x? I get something else with a factor of x, right? Everybody agree with that? And why is it an act? This certainly sucks. It's a vacuum cleaner. Because if I take a polynomial that has a factor of x in it, and I multiply it by some other polynomial, now I've got a bigger polynomial with a factor of x. So this is vacuum cleaner, right? And I can do the same thing here. Now, if I call this I and j, then ij is the thing, is everything that looks like this. X f1 xy times y f2 xy plus x f3 xy y f4 xy and x f2k minus 1 xy times y f2k. That's what a typical element looks like. This is an element of I, J, and you have to add them all up. Now, in this particular example, I can collect the factors and pull an XY out, and that's fine. But in general, a typical element looks like this.
Why, do you go up to F of 2K? The max, like K.
Oh, because I noticed that, because I've got even numbers, right? And I wanted to make sure that I was on an odd even.
Okay.
Okay, so I'll leave that as an exercise, see if you can show that that's an ideal, but it's not too difficult. And I'm gonna give you a big theorem now, and I'm actually not gonna prove this one, because the proof, it's fairly, for practical points of view, with the examples of rings that you'll look at, it'll be pretty obvious that this holds. But in the general setting, this is actually a difficult result. And it requires something called, that's equivalent to something called the axiom of choice. Have you ever heard of, anybody ever heard of the axiom of choice? Basically, so here's kind of our little mathematical fairy tale of the day. The axiom of choice is one thing that one might hope for sets when you're doing mathematics. And basically what it says is, if I have a large number of sets, I can go through these sets and pick out any element from any one of these sets that I want, right? This requires no proof if the number of sets are finite. But if you have a large infinite collection of sets, it starts to get a little bit kind of shaky. Now, one would hope in mathematics that you could pick anything out of any collection of sets, even if they're infinite. And most working mathematicians believe in the axiom of choice. They're very pro-choice that way. However, it does lead to some strange consequences. We're not going to talk about the axiom of choice so much unless you want to come to my office and have me bore you for an hour, which I would be more than happy to do. But I will give you the following theorem that follows from this. Theorem. What are the rings with identity? Actually, for this theorem, it does not have to be commutative. But again, you can, for practical purposes, you can assume that rings are commutative. But the important thing is the ring actually has one. And suppose that you have any ideal in here, proper. Then I is contained in maximal ideal. So any ring with identity has maximal. And one might call this something like this. This is a very fundamental theorem in commutative algebra, actually, that any ring of identity has maximal ideal. Let me kind of talk you through this a little bit. Like I said, using the axiom of choice here is a little bit beyond the scope of what we're going to do. But what this says is, and you might think, oh, isn't that stupid? Because after all, can't you just put I in an ideal that's so maximal? But here's the thing that could go wrong. Suppose that you put I in a slightly larger ideal, and then that in a slightly larger, and that in a slightly larger. And all of these are proper ideals, right? What if that process never terminates? Right? What if no matter how big you got the ideal, you could always make it a little bit bigger, right? And I can give you examples of rings without identity where this actually happens, where you try to make the ideal a little bit bigger, and no matter how big you make it, and it's still contained inside the ring, so proper, there's always one that's just a little bit bigger, right? It's almost equivalent to, let me ask you this, what rational number is as close as possible to the square root of 2? And the answer is, there is none. Suppose you're coming in from below, right? Well, you approximate at 1. Well, now you can do better because you can do 1.4. Now you do better, 1.41. No matter what rational number you pick, there's always another rational number that's a little bit closer to the square root of 2. That's one thing that could go wrong. But if you have a ring with identity, there's always a maximal ideal that I is contained in. And in fact, it says something stronger here. Is got have any proper ideal, then any proper ideal is contained in some maximal ideal somewhere. And so this last statement follows by just starting with I being the zero ideal, because the zero ideal is contained in some maximal ideal. Yes, Con.
So the definition of maximal ideal that we had at the beginning of the lecture, that maximal ideal must be a proper ideal.
That is correct. If we use the terminology maximal, prime, or radical, we're assuming it's a proper ideal.
So there is always, sorry.
Yeah.
So there is always a proper ideal that is less like it's not the entire ring, but it's.
But it's maximal. Yeah, that's absolutely correct. And in fact, it doesn't have to be unique. For example, for the integers, there's infinitely many maximal ideals. 2z, 3z, 5z, all the primes are maximal ideals. Yes.
What does it mean for a ring to have identity again?
It's just got a 1 in it, right? The thing I removed here is it may not be commutative. Like, for example, 2 by 2 matrices over the real numbers, right? It's got an identity. It's basically 1, 0, 0, 1, but it's not commutative. Okay. Let me give you the next definition here. I'm going to tell you what a homomorphism is. We went through this business with homomorphisms of groups, and now the payback is, again, when you're looking at these kind of algebraic mathematical structures, the themes tend to kind of repeat themselves, which is convenient. Definition 7 to 11. Let R and T be rings. So I'm going to define something that's called a homomorphism. R and T is a function. Okay, so now we've got something here, and I didn't use the adjective up there, but I meant to, a ring homomorphism. Well, a ring, first and foremost, is a group. So this better be a freaking group homomorphism. So first thing, phi of R1 plus R2 is phi of R1 R2, or R1, R2, for all R1, R2. And folks, all that means is, remember, R under addition is an abelian group. So all this first statement says is, hey, it better be an abelian group homomorphism, right? Now, what sets a ring apart from an abelian group? The fact that it's got the second operation of multiplication under it, right? So if I want like a homomorphism, if I want that kind of thing that respects the mathematical structure, I better be respecting on the multiplication too. So I want this to respect the multiplication. And that's it. It's just like a group homomorphism with a little extra oomph, right? It respects the multiplication.
But you could not write, for example, phi of R2 times phi of R1. You don't know if it's commutative or am I?
Oh, yeah. No, she's absolutely right. Now I'm assuming that the rings are commutative here in this, but if you were in the more general, you would definitely write this way in the non-commutative section, but you don't know that R1 and R2 are the same, right? So you can't turn these around and you can't turn these around.
But for any ring, you could do it for R1 and R2 because addition is always appealing.
Absolutely, yeah, R1 and R2 you can interchange because addition is assumed to be commutative, right? That's my abelian group part. Good. Right. So, example. P from RT be a homomorphism. And the kernel of phi of R. So this is probably even more familiar, like your linear this, in fact, this is even kind of more like your linear algebra. The kernel of phi is all the crap in R if it goes to 0. This is just like the null space. And in fact, actually, if you look back to vector spaces, when you all did that in linear algebra, a vector space is an abelian group. The null space was just the kernel of that. Well, a linear transformation is a little bit more than an abelian group homomorphism, but the idea is the same, the concept is the same. This is an ideal. Proof. We already know that kernel of phi is a subgroup. Because we know that R is a group, and we've already proved that the kernel of any homomorphism, and remember, first and foremost, this is an abelian group homomorphism, we know it's a subgroup. So, in fact, it's a normal subgroup, but the group's abelian, so normality is a non-issue. All we got to do is show it sucks. That's it. We just got to show it's a vacuum cleaner. So let X in the kernel of phi, and phi of X equals 0. So if R is an R, then phi of Rx is phi of R, phi of X, because it's a homomorphism. And this piece is 0. Therefore, Rx is in the kernel of phi. So it's a vacuum cleaner. It sucked that right in. Okay. Let me give you this one last theorem, and I'll let you think about this for Monday, for next time. Theorem 7. Let R be a range, and I in R an ideal. Number one, the quotient group R mod I. Remember, I, the ideal, is a subgroup of R. So you can do this R mod I crap we did with groups. Notice that since R is an abelian group under addition, that's always normal, so we're good to go. And what this looks like. this quotient group is actually a ring with multiplication given by okay, I just got to come up with a way to multiply two cosets and get a new coset. There you go. He's got it. If it ain't easy, don't do it. And actually, I'm gonna show you this works next time. But you need the fact that I is an ideal. You need that vacuum cleaner to make that multiplication well defined. And phi from R into R mod I given by phi of R is equal to coset R plus I is an onto ring homomorphism. Okay, any questions on that? Any questions? Okay, we'll discuss this and look at some further examples next time. We'll probably finish this up in a day or two, do finite fields, and then we'll spend the rest of the time doing applications.